invertible functions. So let us understand the definition of invertible function. A function f from a to b is said to be an invertible function if there exists a function g such that it's from b to a. So when you take a first function, it's from a to b. Whenever you say that this function is invertible, there should be another function which is g in reverse order b to a, such that when you do composition between those two, g composition f should give you back identity function, a identity function, and g f composition g should give you identity function on b, where a is the identity function on a, ib is the identity function on b. G is called an inverse of f here, and it is denoted with f inverse. G is equal to f inverse. In pictorially, there is a set a and b. A to b, there is a function called f. From b to g, if another function exists, which is denoted with f inverse, such that when you do composition between these two, g composition f should give you back a itself. When you do f composition g, it should give you identity function on b. So that is all about the definition of the invertible function. So we will see the problems, how it is solved using invertible functions. Okay, let a is a function from a is a set 1, 2, 3, 4, and f and g be functions from a to a. It's not new set, it's a function to same set a to a itself. If it is given by f is a function, and there is a mapping between elements of a and a itself. So when you write this in terms of pictorial way, 1, 2, 3, 4, since it is a to a itself, the same element will come here also. Sorry. And according to f function, when you define f function, 1 to 4, 2 to 1, 3 to 2, 4 to 3. There is a function from 1 to 2, 2 to 3, 3 to 4, and 4 to 1. That is g function. You have to prove that f and g are inverse of each other. So from the figure, it's so clear that every edge between the pair is having alternative edge or alternative connection from other end. And you can directly say that both are inverse functions, but you have to show in terms of steps, right? So for that, you have to do like this. G composition f of 1 is defined with its definition. G composition f of 1 can be written as g of f of 1, which is equal to g of, so f of 1 is in 1, for f function 1 is paired with 4. So write that 4 here. and G of 4. In G function, find out 4 image. 4 image is 1. You get the answer 1 here. So you have taken one element and under function you are getting the same element. This is called as identity function. You can just recall identity function definition. If an element is getting mapped onto the same element, then it is identity function. So one is mapped onto one itself. So we have to check for all the elements in the similar way. You can do yourself. G composition F of 2, the second element. G of F of 2, G of F of 2 becomes from this 1, G of 1 becomes 2. So 2 is getting mapped to 2 itself. Similarly, G composition F of 3, G of F of 3, G of F of 3 is 2. So G of 2 is 3. So 3 is mapped onto 3 itself. The last element is 4. G of F of 4 is G of F of 4 is 3. So 3, 3 and F of 3 is mapped to 4. Sorry, G of 3 is mapped to 4. So 4 is mapped onto 4 itself. So this indicates that the results are indicating that it's a identity function on A itself. Therefore, it's G is the inverse function of F. In the similar way, you can also compute yourself the other way of functions. So that is F composition G. You should try to do F composition G for all the elements and find out that even that is also giving you identity function on A itself. Then you can prove that, say that both are inverse functions. Right now, according to this explanation, G is the inverse function of F, that's all. If you prove that this is also satisfying the condition, then it becomes both are mutually inverse of each other.